So welcome back. This is second part of Spalart's and Allmarus model development from their original philosophy and conference papers based on the Baldwin-Barth model and others. And just to remind you, the model development is really in 4 parts, and each part builds on another. And the first part is to look at sort of this turbulent shear front. And then they modify the model to work on High-Reynolds Number boundary layers, meaning the outer layer, then the inner layer of the boundary layer, and then they add in a transition effects. So each part of the model builds on the previous, and it didn't really affect the previous model development, meaning in terms of predictability. So every piece of the model was sort of like added on to try and predict more physics. So we left off with, and I should also mention, remember this model is, so here's the base model right here in 556, which we showed before. And you can see their model they propose is eddy viscosity model, and the B is sub-base, S goes as, say, vorticity, and nu sub T is really vorticity. This term here is production, and there's a diffusion term. So that's the base model. It wouldn't be able to handle something like boundary layers yet. It's just written for this basic shear turbulent front, which I drew in this little picture right here in 557. And they've added in this type of form for the solution for how eddy viscosity varies through this turbulent front. And it's a bit empirical now, because now they're going to be making some corrections to this base model and how it occurs through this front. So here I note that they analyzed this turbulent front and coupled the eddy viscosity and shear rates, and they found that this ratio here, which is right here in the equation 557, needs a little bit of modification. And I noted from the original work that they found that if that value here is larger than 2, then it makes the velocity profile too smooth relative to more direct computations. And if it's less than 2, then I guess good solutions exist. And if it's 1 or less, then it's unphysical. So you see this little term up here, CB2 is a coefficient. So obviously that's already bounded in terms of solutions. So then they just suggest calibration of 1 is less than CB2, so it's equal to 2. This is basically an empirical type process of calibrating coefficients. So generally, you might see in these models, sometimes they say CB2 equals 2, general. But you can go into your own solvers and adjust these how you want for your own solutions. Another variable, nu sub 2, represents a diffusion coefficient, and certain weak solutions can appear for this equation 557, and some of them might be non-unique. So they did some numerical studies and they found that if the diffusion term is rewritten as nu t of nabla 2 nu t plus 1 plus c2 2, a new coefficient, times nabla mu t squared, then the numerical solutions exist that correspond to, I guess, physical flows of the turbulent front. So that's the main point there. So outside these turbulent shear flows, there might be Reynolds stresses. So say there's a boundary layer like this, a wall, a boundary layer of turbulence, and what happens out here? And in these models, you would expect there might be a small Reynolds stresses or no Reynolds stress. Obviously, if it's laminar flow, you wouldn't have anything. But in practice, in these models, there's often very, very, very small values. And these diagonal components do not vanish. And they're often induced by the internal stress or fluctuations, that's pressure fluctuations, or numerics. This is all running in a discretized framework. And ideally, you want your eddy viscosity to be 0 in that region in practice. But in the solutions, you'll find it's near 0, but non-zero, right? So they actually also chose some of these empirical forms up here in coefficients. To make the model insensitive to those small values. So it's not just about calibrating against physics, it's also sort of choosing some empirical coefficients to make the model well behaved. Okay, one last thing is they've noticed that the eddy viscosity sometimes is over-amplified by their production term, which, to remind you, is this term here in 556 of the base model. And they give an example, and they would say, consider a steady flow. And it's past a slender body. So there's like a slender body, and there's U infinity. And the body length might be L. And there might be some small boundary layer thickness delta. So here's some just basic scales. So based on sort of a thin shear layer deformation tensor, we might write U infinity over L. And the logarithm of the amplification ratio will be on the order of, say, CB1 times S. Now, in these thin shear layer algorithms, the amplification ratio for this production term alone would be on the order of, say, CB1L over delta. So for small eddy viscosities, there might be something in the free stream or resulting numerical errors which might intentionally trip flows if they become larger. In regions of high shear, but not trip flows in the free stream. So these are sort of the main notes about, which I kind of extracted from their work for the base model. So this, where we are is like, that's really part one. And now we want to add terms and modify previous terms in part 2 and 3 for the model to work in, say, boundary layers. Because it should work okay in shear layers now because of our analysis of the base model for the turbulent front. So that's where you go into part 2 of their philosophy. And they look at the near wall High-Reynolds number region. So what does that mean? It means we have a turbulent boundary layer, right? And there's the profile, if I might draw it. And there's an outer part and an inner part. And they're going to look at what I guess the community actually calls the High-Reynolds number region. It's High-Reynolds number because it's in the outer part of the layer. So they're assuming it's very high Reynolds number flow. And there might be some blocking effect, much like you have a wind tunnel. A boundary layer grows and it sort of blocks the flow at a distance from the wall, and they view that happening through the pressure term of momentum, and that might cause destruction of the Reynolds stress. So this is actually from one of their papers. So what they want to do to handle this effect in the boundary layer is add a destruction term in the transport equation, which was 556. And they just directly wrote down this term from dimensional analysis. The small w here, excuse me, this is not a u, stands for wall. So that's what that coefficient is. This is just W1. My typesetting's not great. It goes as some viscosity, and D is distance from the wall. So right there is where I would argue that the model is not a closed model, because we're assuming something about the solution. It's a local model because it's not something like calculating boundary layer thickness like Cebeci-Smith's model, but it's before you run your calculation, you got to go to every grid point in your grid and calculate the distance, the nearest distance to the wall. So that's kind of a little bit of a criticism and a little bit of pre-processing in your grid. Now, what's interesting is here, as you see, they put d squared in the denominator as so far from the wall. This term goes to 0. And hopefully the viscosity term will go to 0 quicker. Okay. Now, this is really looking at like a 2-layer model again, and in the outer layer, we'll see that the eddy viscosity scales with boundary layer thickness, and the inner viscosity is proportional just to the distance to the wall. So in the traditional boundary layer theory, the friction velocity, which we use of tau, not use of r, we can write S, which is something like vorticity, goes as u tau times a constant divided by the distance. And also the eddy viscosity goes as u tau times that same constant, maybe it's about 0.4 times the distance to the wall. So for equilibrium flows, which this model is being formulated for production and diffusion terms, will be all positive. And balanced by destruction term in the eddy viscosity model. And that, if that's true, then they can find this coefficient CW1, or estimate it, and it should go as CB1, the basic coefficient divided by kappa squared, plus 1 plus CB, come on, 1, all over, and the Prandtl number. So this is their choice of a function for which they can put into this model, which they would add to equation 556 to have an equilibrium flow. So now they've already calibrated CB1, and they do have this coefficient k and Prandtl number, which can maybe be calibrated a little bit. So what does this mean? This shows that the destruction term this way is actually decaying too quickly in the outer layer of the boundary layer, and so they want to make more empirical correction. Needed because term is too destructive. So what will they do now? They're going to try and give a new calibration. We might multiply the new terms by a function, and they'll call that function FW. Why W? Because of course it's just some wall empirical correction function. So this is what we call an auxiliary function. It's one that's multiplied by the model to correct, I guess, bad behavior empirically. And that's listed in the summary of their model and in D.C. Wilcox's book too, which I'll show at the end of the class in the model summary. So these coefficients, you don't really want to change CW1 because that's what balances, I guess, in theory, production, diffusion, and destruction terms. So you don't really want to change that. So all we really get to play with is some function FW. And we want to choose FW or similar function to match boundary layer measurements in the outer layer, or High-Reynolds Number shear flow. And the question is, how do we do that? Well, I noted that FW is our multiplication function, non-dimensional function, and we want it to be 1 in the log layer. So the outer log layer, Cole's wake region, will be High-Reynolds number. So that's part of the choice. So before we do that, we want to take our function here, CW1 times V over D squared, and FW, and multiply it through and add it into our model. So this is our new model based on the High-Reynolds number. We once again have production, so that's this term, the diffusion terms, and now we have this extra term to handle High-Reynolds number flow for outer boundary layers. So this is where this terms come from. So CW1 is already set through the balance of production, diffusion, and destruction. FW, we need to kind of find or calibrate, and then we have eddy viscosity over the distance squared. So remember, this whole term goes to 0 outside boundary layers because you're far from the wall. So where did they find this? Well, they looked for inspiration from all the previous algebraic models that we looked at. It should go something like what was done in the past from, say, Cebeci-Smith or Baldwin-Lomax. So there's a lot of arguments, and this is a huge part of the paper to get this to work fast and numerically robust. So they defined a length scale. Their length scale, right, is the eddy viscosity is something like meters squared per second. S probably goes, I think, as 1 over S because it's a vorticity. So that's divide. So the S's go away. We get meters squared square root. That goes as length meters. So I think that checks out. So they are going to form a term like this as a non-dimensional argument for some function and propose a new distance r, which is eddy viscosity divided by s. So that's that length scale term. You see nu t divided by s. And to normalize it, they divided by a constant, which is non-dimensional. And that's already chosen earlier, and d squared, that goes as meters squared. So they have length, this is not square root, so that's meters squared divided by meters squared. That gives r as non-dimensional, right? Okay, and they want R and FW to equal 1 in the log layer so that this function is just as it is, but very near the wall, they want it to go to 0. So they can choose really any functional form they want, but it's penalized, so near the wall, it becomes very, very small, and very, very, very far away from the wall, it's also small because the d squared term. So this is where, and there's many types of empirical functions you can choose, but this is the one they choose. So this is their wall function, which is a function of this r non-dimensional distance and eddy viscosity. G is just another correction, and that's a function of r plus some coefficient, some r to the 6. So you see this 6 power appears in many places. You can go through this function and try other powers like 5 or 7, 6.5, it won't matter. It's relatively insensitive to the power as long as it's large. Now, they've made some notes, and this is, this is a huge empirical step, and it might seem to come out of nowhere, but they have some justification. And one is that G to FW is a limiter that prevents large values of the wall function. And it was found through testing. Obviously, G used to be just R here. So they add in CW2 R6 minus R into G. That code behaved better, simply put, and more stable solutions. Typically, R is near unity or 1.1 in practice for regions in log layer. And here they've altered slightly their CW2 function, calibrated against boundary layers, and they found CW2 is set to 3 to have good agreement with a lot of flows. And there's also a calibration coefficient, I think, which was CW2, and that was calibrated against skin friction from an experiment. And I've actually noted the Reynolds number. It was a RE of 10 to the 4th on plate, which is actually a pretty small Reynolds number flow. So that is the modification of the model in part 2. So big picture, this now, equation 558, is their model which handles, right, turbulent shear away from wall, turbulent shear flow front, and it handles High-Reynolds number boundary layers. So you could actually stop here and use the model if you put in a wall function to handle flow near the wall. But they wanted to keep going, and they needed to modify the model again to handle their near wall region. So that's what this part of the flow is. So in the near wall, here's our wall, and the distance once again. And now we want to handle this region, near wall. And sometimes I think that's a little bit easier to handle. And so what's the philosophy behind that? So they need modifications to handle viscous region of the flow, which is near the wall. And they had to introduce a few new little coordinates. Well, they might look at y plus, just like we do, and traditionally people do in their experiments, and also introduce new tilde, which is a modified eddy viscosity. Now, when y plus, or we're very, very close to the wall, this nu tilde will be nu, well, when nu tilde will be different very close to the wall, and nu tilde will be equal to nu very far away from the wall. So they want to modify the eddy viscosity when, say, d is very, very, very small. And so they introduce a new non-dimensional parameter. It's called chi, and that goes as nu tilde over nu. So that's a new non-dimensional parameter. And they also introduced lambda, which is equal to y plus of times kappa constant. So that's just a modified distance to the wall lambda. So this is a problem, but thankfully the hard work, I think, was done by Baldwin and Barth, which we previously talked about, where they looked for transport quantities near the wall, and Baldwin and Barth in their predictions show that eddy viscosity likely behaves pretty linearly near the wall. So we want to modify the solution near the wall. There's other good things for doing this. It's numerically, it's easier to resolve nu tilde near the wall rather than u. That's their statement, and honestly, I'm not completely sure why that's true. Maybe you have an idea. And that means coarser grids can be used away from the wall, which is good relative to two equation models. And so they're going to set out to devise a near wall damping function. That's what it's called in this one equation model world. So based on these parameters, they say that the eddy viscosity is going to go as k times y, which is lambda times friction velocity in the log layer, but not in the buffer layer. So they're going to say nu tilde is going to go as kyu all the way to the wall. And that's good also because that way nu tilde is 0 at the wall, right? Because of the slip condition, u will go to 0 at the wall. So here's the proposed empirical correction. We have, and excuse me, this is nu t, not 5. I don't know why I did that. It goes as nu tilde times FV1. So what does that mean? That means that they are redefining the eddy viscosity in the whole model, and it should seamlessly transition to a different eddy viscosity near the wall according to this function. Remember, chi is nu tilde over nu itself. So looking at solutions, this is an empirical correction to force the solution to behave the way they want it to be near the wall. And they introduce these new coefficients here, say sub v. That means it's a viscous coefficient for the low-Reynolds number part of the model. And they note that there could be lots of different functional forms for 5.61, but this is the one they choose. And they also acknowledge that there's absolutely no basis for using this particular form over other forms that might make the flow well behave and support solutions near the wall. So they looked at these flows, and they could choose a number of coefficients, and they have to choose calibration for CV1. And this isn't originally their empirical correction either. There's a paper, I believe, Meller and Herring, which did the similar function, and they set FV1 to 6.9. And FV1 in the Spalart-Allmarus model, they set it to FV1 of 7.1. So you can see there's even a little bit of difference between different authors making near-wall corrections. It turns out it doesn't matter too much because the eddy viscosity near the wall doesn't have too much effect on the solution through the boundary layer. Now, if we've modified the eddy viscosity in our transport model, and I'll just scroll up for a second, so bear with me. Here it is. We're going to have to do the similar operations throughout the rest of the terms that we previously developed. And that's why when you see Spalart's model in papers and in CFD codes, it often has that little tilde over the rest of the terms. So they first look at and say, okay, well, we need to modify the production term, and they replace S with S tilde. And using the same definitions represented up here in, for, let's see, chi, lambda, and equation 5561, they put in similar operations, and they say, okay, well, S, which goes as vorticity in their original model, will now be defined as S tilde, which we see there. And you can see they've also modified this form here and multiplied by FV2. And FV2 is this function. So this is just taking that empirical model and applying it to the production term to be consistent. So far away from the wall, once again, you'll just reduce to vorticity. Very, very close to the wall, you will having an effect of this modified eddy viscosity. So FV2 is another function, which is constructed just to be consistent with the near wall model. So it turns out the problem with this new model right away is you can see there's D in the denominator, and this term is really important near the wall. In fact, at the wall, D would be 0. But it turns out eddy viscosity is also 0 at the wall. And turns out that was a choice they made. It's numerically well behaved. So you can imagine reading that kind of worries me, because if I was going to implement this model in code, I would say, well, there's D in the denominator, and I have a, 0 distance, and it's a denominator, and my code's going to crash. Well, it turns out at the wall, you would just set that whole term to be 0, and in very small distances away from the wall, you would actually have a distance calculated, but your eddy viscosity would be much smaller, so that term on the right-hand side of S would still remain small, so it's well behaved. So the eddy viscosity is always much smaller than, say, D squared. And D squared can be extremely small. But your grids would be way more coarse than like a standard K epsilon or K omega model. Okay. Other terms that we talked about before also need to be modified. For example, we talked about R, and R might go as nu tilde all over S tilde K D squared. Just like that, as one example. So this is part of the process of building up these types of models. I've already talked about this boundary condition. At the wall, you set eddy viscosity to 0. And so eddy viscosity is sort of quantity. It's an empirical correction, like as if the fluid was in a different state of matter. It has a different viscosity. The turbulent flow is a different type of material, if you will, in these types of models. And you would say, well, for boundary conditions, if I develop a new transport equation like for eddy viscosity times omega, which is what Spalart's model is, you would say I need to rigorously develop through like maybe partial differential equations theory some new boundary condition. They didn't do that at all. They just said basically eddy viscosity is 0 at the wall, and they wrote by analogy. Maybe other terms. It's also a choice or stability. And there's no like rigorous analysis that I can find or know about that sort of justifies this, other than it works really well. So after making all these choices, a bit of hand waving, choosing some functions, running lots of simulations, comparing to hundreds and hundreds of different flows, they found this model. And this is the model, the third part of the model without tripping. And it turned out that at the time, a lot of the earlier models were just setting eddy viscosity to 0 before like a transition to turbulence and letting it be non-zero afterwards. And so they would have to choose a tripping point. So they wanted to do something more different and maybe more advanced and modify the model one more time in the fourth part to try and capture transition, which is really, really hard to do. And in their paper, the original one, the conference paper, they made some funny statements. Well, not funny, but ones that I found really interesting even today. And that way their model might be able to handle laminar flow, transitional flow, and fully turbulent flow. So let's look at some of those motivational statements. So first, they found this final set of equations, and it handles laminar flow, and they want to still determine where transition is. And it still needs some input from the user beyond just like a transition point. Like that's really what you want to predict. So they looked at the earlier codes where there's algebraic models, which we talked about, and they usually have that on-off switch, which I just mentioned. So if it's an eddy viscosity type or length scale type model, they just say, oh, well, you know, the turbulent terms are 0 for laminar flow. And then at some point in the flow, you would just let them be non-zero and let the model evolve, and that works fine. You could even do that in your fourth computer project if you wanted to. But they wanted to go further. And these models also require usually some kind of structured grids because they're algebraic. And they wanted a model that works on unstructured grids, because they were at Boeing eventually and wanted to do real flows, not just boundary layers. And in the fourth model, T will be trip as their new subscript. And they note themselves that turbulence models shouldn't be trusted to predict transition, which is a powerful statement to write in your own paper when you're making a transition model. And they also want to handle relaminarization, where a turbulent flow, as it progresses, might decay and become laminar again. So they want to handle both these cases in the same code seamlessly. And they want to try and introduce a new function, say ft2 for t is trip, which I mentioned. And they apply this to thin shear layers. And they think about thin shear layers because maybe you have a free shear layer, or maybe you have a boundary layer. So transition should only happen in their model in those situations. And that makes sense, because if you have like an airfoil, you imagine there's a stagnation point, and there might be a transition point on the top and bottom as the flow goes over. So what they did is they took equation 563 right there, and they did a linearization of it for small eddy viscosities, nu tilde. And then they showed it only really contains a production term if you do that, or they argued. And near nu 0, they would call that the unstable solution, going in, say, the x direction, as an example. Okay. So in these boundary layer codes, there'll be a 0 solution can be obtained, but exactly non-zero values in the numerical solvers are usually never found. So they would argue that the transition occurs, is driven by numerics instead of physics. And that's transition and the transition point in wind tunnels, for example, is very hard to predict where it's going to occur. So if I take the same model and run it in two different models at the same speeds, it could be that the transition occurs at two different locations, and that's very typical. So it turns out this is a stable solution, and somehow they have to define and create a new model to try and at least predict a transition location. And they wanted to do that with sources. Okay, so if, say we have a, I'll just zoom in here to make the diagram. Say we have a wall, and this is maybe an airfoil. So this is a stagnation point, U equals 0 here. And the flow is laminar and turbulent. Well, there's a transition here. And usually in these codes, you would say, well, there's some X location. Actually, I should do that in orange. Downstream. And that's where the transition point is. Instead, they decided to use more of like a Gaussian model, more of a statistical model, and say, okay, well, there's this Gaussian envelope, and that's like a source term for transition. Now, in three-dimensional flows, they would actually make a Gaussian envelope about a line that goes along the wing of the plane or airfoil. In 2 dimensions, they would just have 2 points, right? One above and one below on the pressure and suction side, respectively. So they would also have a Gaussian envelope here. So what would that mean? They got to ask the user to now specify the location of this like Gaussian envelope to simulate transition. And then, if they want to work on like a High-Reynolds Number wing, like at Boeing, and run their Spalart-Allmarus one-equation model on it, they would have to have some insight from the experimentalists. And so experiments never go away. So to kind of calibrate this envelope and set its location as lines on the upper and lower surface. So imagine setting up a CFD code of a wing. You'd have to basically specify on the wing, on the surface grid, basically some parameters or lines with envelope width and location. And that would be sort of based on an experimental insight. And then you could vary the wing to do design. So how they're going to do that, they are going to take a term that looks like this. So there's your function for tripping. This is a coefficient. And here's your Gaussian envelope type function with another coefficient which needs to be calibrated. And there's your sort of function, capital theta, I think, in this LaTeX package I'm using, which is centered about here and goes in the left and right direction. Okay. So it's a little bit beyond the class, but they're using and talking about attractors. And well, I guess we talked about it a little bit in our first computer project on Lorenz's theory. But this is just the general function, and they want to move it into their main model. And they notice that when they do this, there'll be sort of like stable and unstable values. Which lead to decreasing and increasing values of their eddy viscosity, tilde, with S, tilde. Right, so of course larger values are going to lead to turbulent flows. So this is in like the good thing about this type of model is it's like a gradual transition, and it's not like instantaneous like you would if you just have a hard cutoff of saying eddy viscosity 0 before your transition point or not. What they do is they go through with this type of model and try and calibrate some of these coefficients, and they found that CT3 in their numerical studies must be larger than 1. And of course, CT4 has to be greater than 0, or else that wouldn't be a function that looks like the ones I've drawn. And they've also kind of had to balance these to have an equilibrium flow energy budget, which they worked hard to get in the third part of the model. So, I've already noticed, or mentioned some of these earlier, and in their modeling and moving this into equation, I believe 556, they wanted transition to occur smoothly, which to me makes a lot of sense in like an elliptic or subsonic flow. You don't just see the flow becoming instantaneous laminar to transition. And this like domain of influence should not extend outside the boundary layer. And they say and argue that omega t delta u, which is the mean flow quantity, is the norm of the difference between the velocity at the trip and the field point under consideration. And they also introduce a new distance, or a second distance, which is the distance from the trip to field point. So just to give you an idea, there's a wall, and at every grid point, before you run the code, say this is where your Gaussian envelope is centered, you would have, say, distances to every grid point, that's d, or maybe d upstream, this would be dt. So you're actually calculating two distances now to do a wall function. So dt is the distance for the shortest line that links the wall locations to the field trip point. And another problem with this approach is that if you have an airfoil in 2D, your code might get confused between the distances of trip points between the upper and lower side of the surfaces. So you also have to calculate that and be careful about that, especially in unstructured code. So let's look at the modified model where they've added in the trip location. That's what this term is here. Everything else looks similar, except now they have FT2s throughout the model. So FT2, FT2. So this FT2 has to be some function of the trip variables, and it's also an empirical function, but it uses the Gaussian form, which we talked about earlier. So here's FT1. It goes right here. And L is just length along the body. So, and also they just put a little minimized limiter here, this G, and grid spacing. So you see, this is just an empirical function that encompasses this Gaussian function to try and mimic transition smoothly in a flow. And this works really well. But you see, the base Spalart model today is really up in 5.63, which is S tilde nu tilde. This model completely modifies the whole model. Just like we, in part 3, we modified the rest of the model to be consistent near the wall, they once again had to modify the rest of the model to be consistent for transition. So this FT2 term here, if there's no transition, we would just set it to be what? 0, because that way we recover the original Spalart model. So you open up a code like Fluent or Star CCM or some commercial code or any number of codes, they almost all have Spalart's model program now. You could turn on and off the transition model. And so when you're clicking that button, really what you're doing is turning it on and off FT2 in the general model. It's that simple. But I don't think it's too good to talk too much about their first transition model because there's been tons and tons of papers and research over the last 30 years since their model introduction on transition, how to modify like Spalart's model in transition. But I think the model's interesting because they introduced this idea of a Gaussian envelope. A few quick notes about this envelope is it's, of course, continuous, which I already mentioned. And I didn't talk about calibration at all. So their calibration, let's just make a few notes about that. So say you constructed these empirical functions, and you have lots of coefficients and knobs to play around with. How would you calibrate it for transition? What would you do? Well, thankfully, as someone doing turbulence modeling at a large company and NASA, you have a large team of experimentalists from some of the best wind tunnels in the world. And there's a consortium of the Air Force, NASA, multiple universities, and they all got together and they had a large database of experiments, transitional experiments, where at different speeds, different shapes and everything. And they also had a large database of transonic airfoil measurements. And so they took a lot of these and they made grids and set the boundary conditions and calibrated these coefficients against a large number of experiments. And that's where the terms came from. So most coefficients in practice are calibrated against experiments. And they included boundary layers, airfoil, transonic airfoil, and a few others. And some of them had compressibility and shocks, and they were over large speed range. But still, it's up to the user to define some of these coefficients. Okay. Here I want to summarize the major modeling. Oh, maybe I'll let you finish that. Sorry about that. Give people a second to finish writing. So I don't think the transition part of the model is key, and because of what's happened since then. And this isn't really a transition modeling class. That's a lot goes into that too, I think, with instability theory. But other people looked at this model and they looked at the first three parts and called that what might be like the major contribution to Spalart-Allmarus in their eddy viscosity S model. And D.C. Wilcox, in the summary of his books, which I repeated here, rewrote their model this way. And you might look at this and feel like it's a little bit more concise. Spalart-Allmarus set out to develop their model and explain it in pieces to people and the community like that, because they could understand logically how they built it up from like a free shear layer to a High-Reynolds Number shear layer and near wall model, and how to modify it for transition. And it could run on unstructured meshes. It was fast because it was only one equation, not two. And it needed less grid points because you didn't have to totally resolve the wall like a Kaplan or Omega model. And so here's the summary of Wilcox. And he says, well, it's an eddy viscosity model for one equation. Here's the one equation, of course, right? One equation model, one PDE. The eddy viscosity goes as eddy viscosity near the wall. So this goes into the momentum equation, right? As an example, nu plus nu tau. And this is the one equation model for nu tilde with S right there. So this is your production term once again. And there's your diffusion terms and your destruction term. And another good thing about this model is it's incredibly easy to program, which wasn't true for a lot of the models in the literature. So that also helped the community buy it. And you can see the model has a number of coefficients, And you know what they are. This is base 1, base 2 coefficient. So these are kind of calibrated like we talked about, and here's the auxiliary functions. For example, this is near the wall. We talked about this one, for example. So you can see, oh, and down here is a more general definition of S. So this is the form I think people, after the introduction of the SA model, probably looked at programming a little bit more. And it's nicely laid out. So you see S in the original model was just seen as maybe like a vorticity, two-dimensional in its original formulation. So this is generalized for 3 dimensions too. Some final notes. Let's see here. Once again, D is distance. Omega ij equals 1/2, as I should write it out, partial ui, partial xj plus partial uj. Whoops. It's not plus. Minus partial uj, partial xi. So that's a rotation tensor, which we've talked about before. And you can see the distance d in its calculation just happens once before the solver starts. And the eddy viscosity equation depends on d. And that's, to me, one argument that it's a non-closed model. Even though people like Baldwin-Barf argued that their model's closed. You might note that the Baldwin-Barf model didn't require like a distance calculation or knowing something about the solution in advance. So even today, there are some arguments in the community about what's a closed and unclosed model. One last point is as d goes to infinity, what happens? That means you're far away from a solid boundary. But when that happens in this formulation, there's no decay of eddy viscosity in a uniform. So there's a huge criticism, in my opinion. So what if we have like a wind tunnel, and in the wind tunnel there's turbulence? Now I would set my upstream boundary condition to have some sort of incoming vorticity and eddy viscosity. And I could calibrate that maybe somehow with a wind tunnel measurement, even though I have no way of measuring eddy viscosity. So from the wind tunnel entrance to my model, I would have no decay of turbulence K, for instance, in the flow. But technically, that should be captured by 2 equation models if we work hard. And so this is one of the things that has often been looked at and tried to be improved in later models of SA. And I should note that if you look up the publication list of Spalart today, who's still active in the community, there's been many iterations of this model to improve it. Okay, so that's where I'm going to leave one equation model, and probably the most used model today is Spalart. And how about we just take a few minutes break to 12:55, and we'll look at his paper briefly and look at some of the results of the model.